All right, got some game week build review for March 24th. This is progress over the weekend. I created a initial level called Void Diver, and the premise of this level is you're a guy with a jetpack and probably a helmet eventually, and you're exploring a space cave. So there'll be aliens, and the terrain will be hostile, and all kinds of interesting, hopefully, stuff like that. So my starting point for all of this was to get tools built for implementing a dual grid system. And I first found out about the dual grid system by watching this video from Jess Codes. It's a year old? Yeah, about. Not quite. Um, anyway, in this video, she lays out all of the problems with the classical grid setups where you have essentially a tile for every combination of edge, and you end up with the borders that go inside the tile or outside the tile if you are doing it a little differently. But in general, you end up with kind of an overlap that's kind of strange and a huge number of tiles to build. And with the dual grid system, you lower that to you lower it to 16 tiles. The boundaries go through the middle of the tile, which is very interesting. And the way they overlap is essentially you define your, there we go. Yeah, so you define your terrain. So in this case, there's grass and dirt. Wherever there's grass, typically you would render a grass tile with the combination of edges that match the neighbors. And with the dual grid system, you actually render the offset area of each corner of each piece of defined terrain. And so that looks about like this, where this is a defined piece of terrain, and these are the corners, and so the corner grids are where you would actually render sprites. So instead of rendering a single sprite for this terrain, you're actually rendering 4 to get the corners. And the video's kind of complicated. I had to watch it like 600 times. And I have implemented this before in Pico 8 and Kotlin for some just playground ideas. So this is the first time I did it in Ruby and Dragon Ruby. So I started in PenPot, just taking the example grid and smashing it into my own. I just used vector boxes and kept it pretty simple, just some very basic curves trying to hit the middle of the tiles, and exported that sprite sheet. Then made a Ruby helper that lets me quickly render my sprite sheet directly to a grid on the screen, and these are all grid coordinates now, not just XY positions. So had to do a bit of translation there. Also, Dragon Ruby starts 0, 0 down here, so there's a little bit of a flip maneuver, but it all works pretty well. So I got a sanity check that I can render my sprites for my sheet into the right grid coordinates, so that was fun. Generated a couple platforms, then generated placeholders where my sprites will be rendered, and you can see we have a natural overlap if we have neighboring squares, so refined that a bit to take out duplicates. And now at this point, I really wanted to make sure I understood exactly how each overlap would be calculated and how I would quickly find the matching tiles for platforms. So you don't want to be looking up out of your array of tiles. You don't want to be looking up by array combinations. And so what I did is stopped my loop at 1, so I ended up just seeing a blue box with the 1 corner, and then focused on getting my 0, 1, 2, 3 in place, which will become SSSP. And the reason that's interesting is if I keep the same order and orientation, then I can quickly do edge detection on each sprite piece, then convert that to binary. So that looks about like this. When we get SSSP, that's 0001, which is hex 1, and you can see how all those behave. So SPSS is 0100. And by basically encoding the hex value into each of my sprite definitions, I ended up with essentially 16 tiles with simple hex representation. And when I loop through each platform tile, I can look for the sprite locations and, one, efficiently make sure I'm not re-rendering a sprite twice, and two, very quickly look up the right sprite to use and just put it in place. So this actually turned out to be very fast once I worked those bits out. And you can see here I just generated a couple platforms, and these have neighboring corners, so it automatically picked up the right corners and then did all the business it needed there. Now this got interesting because the edges are in the center of the tiles. We're defining our platforms and then drawing on our corners basically. So it took me a few minutes to wrap my head around exactly how to get the collision detection to work. What I ended up doing was simply defining my platforms as my collision areas, and then I had to do some adjustment on my player because he was sinking into the tiles. To figure that out, I rendered the actual hitbox around my player and found that it was just way out of whack. So I got that tuned in and adjusted my contact collision formulas and all that stuff. And so you can see here, very, very simple. When we render these, when we render the corners to get all of these bits, it doesn't matter because our collisions are just the defined platforms. So the corner you see here is nice and smooth, and that's partly, well, it's exactly because we're using the offset grid to actually render the tiles, but the platforms are the collision areas. And I've got my collision area for player worked out pretty well here too. So then I generated some terrain using kind of a walking randomized surface algorithm, and it just picks a max min and then kind of walks around and randomly-ish places things. So we'll take a look at what that becomes over here. Get my controller to connect. All right, so we're in the level, and if I hit select, this is another thing I added, this debug business pops up, so I can see the outline of everything, and you can see my jetpack physics, and we fit into there, and we've got good, you know, it's not bouncy. That's another thing that can happen with edge detection and collisions is because you have gravity and velocity and such, when you come down, often you'll bounce. And there's sometimes where you'll bounce and sink, or bounce and just kind of bounce above indefinitely, and that gets kind of crazy. But this is actually working really well. In this debug business, which is another part of my update from the weekend, this should be applicable to any level, and it throws up the overlay with the controller. So as you push buttons on the controller, and I'm just using one of these little guys, but as you push buttons, it lights up. You register the debug into your level, and then you can register individual components into the debug from there. So my player is being registered into debug. Player has debug outputs of a lot of its properties. So as things change with the player, it automatically goes into the debug. And if you want to add a property or anything like that, it's pretty simple just to add it to the hash. The other kind of cool thing is the debug then registers into the player as well, and so there's another layer of possible debugging where you can just do things on the player itself and not just on the display for the debug business. So anyway, you just press select to get that to show up. So that should be a lot of stuff we can reuse. All of the code for the dual grid it ought to be reusable, whether it's a side scroller or top down or any other kind of game. It'll work whether you have ground and platforms or any other combination of things. I need to get, you know, obstacles and all that kind of stuff in here, and once I do, then we should have quite the variety. So the 16 sprite high. The 16 sprites might become 32 if we're adding a whole different combination of terrain, which makes total sense, and that's totally manageable. But anyway, should be all reusable and awesome and fun. To our notes, let's see here. I think I talked about all that and that. Physics side was kind of interesting. When you launch with the jetpack, it has a bit of acceleration as the jetpack kind of like heats up, and then as you come down, you kind of got to feather it down a little bit. I want to add some kind of visualization for that so you can see. And then of course he'll get injured if you come down too fast, and there'll be like fuel levels and all that kind of stuff. Now, when you're on the ground, there's more friction left and right because you're walking. And when you're in the air, it's obviously very floaty because there's a lot, there's no resistance when you're in the air. So that was a fun little bit to get the ground detection to then influence the friction. Just really fun overall. So yeah, I'm giving this a Funprovement score of 4 out of 5 superstars. And this will be in the pull request, so hopefully you can take a look. Thanks.